non-coherent differential phase shift key. So we have already seen non-coherent DPSK. Now differential phase shift key. As the name implies, it is either there is a differential encoding of that binary input as well as there is phase shift key. That is differential phase shift key. So here what we do is, if I have a symbol 0, consider we have a symbol 0. So what we do is, we phase advance the current signal by 180 degree. So if I get a symbol 0, I have to send a symbol 0, advance the phase of the current waveform by 180 degree. If I have to send 1, leave the phase of the current signal unchanged. For example, consider now my DPSK signal is root of EB by 2 TB into cos 2 pi SAT, and this is my signal for the duration 0 to TB. Okay, now consider I have a symbol 1 for the duration TB to 2 TB. That is, for the duration 0 to TB, this was my signal that was transmitted. This was my transmitted signal. And for the next duration, that is TB to 2 TB, I have to transmit a binary symbol 1. So as I said, if I have a symbol 1, I leave the carrier phase unchanged. That is, originally for 0 to TB, let this was my transmitted symbol root of EB by 2 TB into cos 2 pi SAT. So when I have a symbol 1, I should leave the carrier phase unchanged. So the same symbol, that is the same transmitted signal, will be transmitted for the next time duration as well. So for TB to 2 TB, I will be having the phase unchanged. So for TB to 2 TB, again I am having root of EB by 2 TB into cos 2 pi SAT. Okay, now you consider the other, that is the symbol 0 is to be transmitted. Okay, so you consider the case symbol 0. For 0 to TB, let root of EB by 2 TB into cos 2 pi SAT was my transmitted symbol. So 0 to 2 TB, this was my transmitted symbol. Now I have to transmit symbols, binary symbol 0. So when I have 0, what do? I advance the carrier phase by 180 degree. So 0 actually corresponds to advance the carrier phase by 180 degree. So this was my original signal. So when I get a 0 for interval TB to TB, that is for the next duration TB to 2 TB, I will advance the phase by 180 degree. So this was my signal. I advance by 180 degree, I will be having cos 2 pi SAT plus pi. Okay. Now the bit error rate of DPSK, bit error rate is given by half into e raised to minus EB by N0. And there is no need for derivation, just know the expression for the bit error rate. Then how we do the generation of a DPSK signal, or how we detect the DPSK signal. So first we move to the generation. So for the generation of a DPSK signal, you first consider binary sequence BK with the binary sequence A 1 0 0 1 0 0 1. This is my binary sequence. Now I have to generate the differentially encoded signal DK. Okay. So for differentially encoded signal DK, first I consider a reference bit. So here I consider my reference bit is 1. Okay. That I just take this as 1. Reference bit is 1. So for the time being, you leave this DK minus 1. In time being, you just leave this DK minus 1. I consider the binary sequence BK, then the differential encoded sequence DK. I consider the first reference bit as 1. So how you are going to differentially encode the signal is, if the incoming binary signal BK is 1, you leave the symbol unchanged. And if the incoming binary signal BK is 0, you change the symbol with respect to the previous bit. Okay, so this is the condition. Now you see, first I have the incoming signal 1. So as I said, when the incoming signal is 1, you leave the symbol unchanged. unchanged. That is, earlier my differential encoded signal was 1. Okay, this was that I assume. So you leave it unchanged mean again you will be having 1. Okay, now you have the next incoming binary symbol is 0. Okay, so when it is 0, what do? You change the symbol with respect to the previous bit. You have to change the symbol. Okay, so your previous, now you have 0 is your binary symbol. Your previous differential encoded was 1. So you have to change it. So you have 0. Okay. Now again your binary symbol is 0. 0 means you have to change it. So your previous encoded was 0. You have to change to 1. Okay. Now your binary is 1. 1 means remain in the same state. Okay. So already your encoded bit was 1. So you remain in the same state 1. Now again 0. 0 means change the state. So earlier was 1. You change to 0. Again 0. 0 means change the state. Earlier was 0. You change to 1. Then 1. 1 means remain in the same state. So earlier was 1. You remain in the same state 1. Again 1. So remain in the same state 1. So this you get the differential encoder signal. Now you have to draw the generator generation, how to generate this DPSK signal. So when I draw the generator block diagram for the transmitter side, you can see when you have the binary sequence BK, you can use a logic network in order to generate the differential encoder sequence DK. Okay, you have to generate this DK from BK. For that, you can use a logic network. So just again go to the table. You can see this is my DK. Just write DK minus 1. Just write DK minus 1. So what will be your DK minus 1? DK minus 1 is a shift this to the right by 1. Okay. So shift this to the right means this 1 will be shifted out. Okay. So you will be having 1 1 0 1 1 0 1 1 1 1 0 1 1 0 1 1. That will be your DK minus 1. Now you see what happens when you modulo 2 add these BK and DK minus 1. When you add 1 1, you will be getting 0. Modulo 2 of 1 1. That is, if you have only 1 1, your modulo 2 operation will give the output as 1. Okay. So here you have 2 1. So the modulo 2 will be 0. When you take the complement, you will get 1. So 0 1 modulo 2 is 1. When you take the complement, you will get 0. 0 0 modulo 2 is 0. When you take the complement, you will get 1. 1 1 modulo 2 is 0. Taking the complement, you will get 1. 0 1, that is, we are having only 1 1. Only 1 1 means modulo 2 output is 1. So when you take the complement, you will be having 0. So from this BK and DK minus 1, you can do the modulo 2 operation and take the complement to get DK. Okay, so that is what we have implemented in this figure. That is, DK is the complement of modulo to sum of BK and DK minus 1. So you have BK and you have a logic network to get DK. When you give one delay, you will be getting DK minus 1. So you have the logic network. The logic network is doing modulo 2 of these two and taking the complement to get DK. Then the remaining block diagram, as we there, you will be having the amplitude level shifter and you have the product modulator root of 2 by TB equals 2 pi of CT to get the DPSK signal. And you see, whenever I have 1, wherever I have 1, I use the transmitted phase. Transmitted phase is 0 degree. Wherever I have 0, the transmitted phase is pi. So all the ones corresponding to all the ones, my transmitted phase is 0. Okay. Whenever I have 0, 0 means we have to advance the phase by 180 degrees. So you have pi. Corresponding to 0, you have pi. All of the ones are in transmitted phases 0 and all the zeros is having the transmitted phases pi. So you can draw the transmitter. Now when you go to the receiver side, what does the receiver do is, the receiver we'll check the, if you consider this is my received signal. Consider this is my received signal. That is, it is having a amplitude A. A represents the amplitude, and the received signal points are A cos theta, A sin theta. We have the A cos theta and A sin theta. We just represent this in a signal space diagram. That is, we have the in phase component as A cos theta and quadrature phase component is A sin theta, and minus A cos theta and minus A sin theta. This is minus A cos theta and minus A sin theta. So this is a signal space diagram where we have the received points. These are the received points. So theta is our unknown phase. Theta is a unknown phase, and A denotes the amplitude. Okay, let this be my received signal that I plotted in the signal space diagram. Then how I am going to find out the symbol is, you receiver first measures the coordinate of the in phase component and the quadrature phase component, that is xi0 and xq0. Similarly, that is at time tb. Similarly, at time 2tb, again it find out the in phase component and quadrature phase component. Okay, so what we say is, if at time tb and time 2tb, you have to check whether there is a change in phase or whether they are on the same phase. That is what you have to check. So at tb, it measures this coordinates. At 2tb, again it measures its coordinate, and it check if I have two vectors, that is one at time tb. At time tb, I use the suffix, I have the in phase and quadrature phase component at time tb, that is I use the suffix 0. Okay, and at time 2tb, I have the in phase and quadrature phase component, I use the suffix 1. Okay, and these two will be in the same phase or are pointed in the same direction if their inner product is positive. That is the condition we are applying here. So we have to check whether there is a change in the phase or whether it is in the remains in the same phase. Okay, so these two remains in the same direction or in the same phase if their inner product is positive. So what I do is, I take the in phase component at the instant tb and instant 2tb. Instant tb is 0, denoted as suffix 0. Instant 2tb is denoted as suffix 1. I take the inner product of these two. So I will be having xi at tb into xi at 2tb, that is 0 and 1, plus similarly the quadrature phase component at tb and 2tb. And if the inner product is greater than 0, I take the decision in favor of 1. Okay, and if it is less than 0, I take the decision in favor of 0. Okay, that is, if it is greater than 0 means they are pointed in the same direction. Okay, they are pointed in the same direction. And if it's less than 0 means there is a phase, they are not in the same direction, or symbol 0 is transmitted. So that is shown in the block diagram here. Now you refer the block diagram. I take the in phase component and I take the quadrature phase component of your received signal. So I have the in phase component, I have cos 2 pi of ct to get the in phase component. Similarly, I get the quadrature phase component. Okay, I have the integrated and get the output. Then what I do is, for the in phase component, I give a delay tb. So what I get at the multiplier is, I have the in phase component at time tb, and again at time delay tb means in phase component at time 2tb. So these two I will find out the inner product. Similarly, I have the quadrature phase component. Again I find out at 2 instant, and add these two. I take the inner product and I check whether the inner product is greater than 0 or less than 0. Based on that, I am taking the decision. That is shown in the receiver block diagram. Okay, so you have to write till this. That is, in phase, the inner product should be greater than 0. You take the decision in favor of 1, else you take the decision in favor of 0.